We're looking at problem number 4 from a previous exam, an exam from 207 in summer of 2007. Problem 4 says we want to find all of the different powers: real power, reactive power, apparent power, and then the power factor of the two different loads, load 1 and load 2. We're also asked to find the power factor seen by the source, which really is the power factor of the two loads combined, and we're given the two impedances of those loads, load 1 and load 2. We're also given the source voltage, 60 at 0 degrees, and it's an RMS. And if you look at this, this is really just a single mesh problem, which once we found that mesh current, we should be able to find the voltage drops, V1 and V sub 2, and from those we can use our complex power formula, VI conjugate, to obtain the complex power. And the complex power is made up of the different parts: our real power, our reactive power, and we can find the angle of that complex power, take the cosine of that angle to obtain the power factor. Let's then look at finding the current, its phasor form, I sub S bar. To do that, we can combine the two impedances, Z1 and Z sub 2, to obtain a total impedance. The first impedance is 2 minus J. The minus sign is telling us that it's probably capacitive, and it is, in terms of its net effect. The Z sub 2 impedance is 1 plus J5. Those have already been written, those impedances, in rectangular form, which allows us to fairly easily combine the real parts and the imaginary parts to obtain 3 plus J4 for our total impedance. This is now 5. The imaginary part is bigger than the real part, and we would think then that our angle would be a little bit larger than 45 degrees, and our angle for theta sub t is then the inverse tangent of 4 over 3, where the magnitude is the square root of 3 squared plus 4 squared, or 5, and this angle becomes 53.13 degrees. Our generalization of Ohm's law says that the total voltage, which is our source voltage, divided by the total impedance, will give us our current, or V source is equal to Z total times I sub source. We want to find I sub source. This was then 60 at 0 degrees. That was our source voltage, V sub S. Our impedance that we just found was 5 at 53.13 degrees, giving us our current going through all of the series elements. I sub S is a magnitude 12 at an angle of 0 minus 53 degrees, or minus 53.13 degrees. Now that we have I sub S, we can find the different voltages, the voltage drops in phasor form across the two loads. V1 is just Z sub 1 I sub S bar. Z sub 1 again was 2 minus J1, and I sub S is 12 at minus 53.13 degrees. Or, if we now convert that impedance into its polar form, we have a magnitude a little bit bigger than 2, which is 2.236. At an angle, it should be a negative angle, and it should be an angle less than 45 degrees, since the imaginary part is less than the real part. It's an angle that has an inverse tangent of 1 over 2, and that's minus 26.565 degrees. That now is multiplied by our current. Now we can take the product of the magnitudes and add up our angles to obtain a phasor voltage drop across the load 1 from left to right using the passive sign convention is 2 times, or 2.2 times 12, a little bit more than 24, or 26.832, at an angle that's the sum of 26 and 53 in the negative direction, since they're both negative, and that's minus 79.695 degrees. That's now our voltage V sub 1. We can find our complex power for S1. That's simply V1 times the current through that load's conjugate, which is I sub S star. V sub 1 is 26.832 at minus 79.695 degrees. That's multiplied by our current's conjugate, which is 12 at 53.13 degrees. Or this now becomes, for our complex power, we have a value of 25 times 12, or 26.8 times 12, or a little bit more than 300. So we have 321.98 at an angle of minus 26.565 degrees. We now can identify our apparent power, but let's not get too carried away. Let's go ahead and just finish this by looking at this complex power in rectangular form, taking 321 or 322 times the cosine of minus 26 gives us 287.99. That's our real power for load 1. We'll have 322 times the sine of minus 26. That gives us a negative J 143.99, and that's our reactive power. And we can now write all of these down. We can say that P1, our real power, is 288 watts. Our reactive power, Q1, is minus 144 volt amperes reactive, or VARs. Our apparent power, which is the magnitude of S1, is 322 volt amperes. And our power factor for load 1 is actually the cosine of this minus 26.565, which ends up being 0.894, and we need to tell you a little bit more about that based on the sign of that. Since it's negative, this is actually a leading power factor. That's part of the problem. That's now the first half, really, for load number 1. We can now look for load number 2, exactly the same steps that we did before. We can find V sub 2, which is the impedance of load 2, 1 plus J5, times the current through that load, which is a series current, so it's the same current that we had going through load 2. That had a magnitude of 12 and an angle of minus 53.13 degrees. Again, we can convert this rectangular form of impedance into a polar form. It should be a little bit bigger than 5. It's 5.099 at an angle that'll be bigger than 45, less than 90. It'll be the inverse tangent of 5 over 1. It's going to be 78.69 degrees. That particular impedance is inductive or lagging. We now multiply that by this current, forming that combination. We have 5 times 12, or roughly 60. So we have 61.188. We add the angles. We now have 25.56 degrees, and that's now our voltage across load number 2. We can use the voltage and the current to obtain our complex power for load 2. complex power is the voltage times the conjugate of the current. We now have 61.188 at an angle of 25.56 times the conjugate of the current. We now have a positive angle associated with our power. The apparent power in terms of its magnitude is going to be 61 times 12, or that's going to end up being 734.26. Our angle is going to be roughly 78.69 degrees, and that's our complex power, which again, let's go ahead and break that down into its rectangular parts, the real part and the imaginary part. The real part being 734 times cosine of 78, or that will then be, for S2, not very much, because the cosine of that large of an angle is not going to give you much of a number. So we have 144 plus J, and the sine of that is going to give you something pretty close to 1, where you now have S sub 2 is 144 plus J 720. That then gives rise to the following powers for load number 2. We have the real power, P2, is 144 watts. We have our reactive power, Q sub 2, which is 720 VARs, and that's a positive 720. We also have the apparent power, which is the magnitude of our complex power, and I believe that was 734 volt amperes. And our power factor for load number 2 is the cosine of the angle, which was 78.69, and that's 0.196. Because of the positive angle, that was a lagging power factor. That's part 2 of the problem. Now we need part 3, which is really the power factor of the total of the loads. We can obtain the total complex power by simply adding the two complex powers, S sub 1 and S sub 2. For adding complex numbers, it's probably convenient to express those in terms of their real and reactive parts or in rectangular form. S1 was 287.99 minus J143.99 plus 144 plus J720, and we're left with 432 plus J576 volt amperes. We can now find our total angle, which we'll call theta sub t, is the inverse tangent of the imaginary part over the real part. That's going to be an angle a little bit bigger than 45 degrees, which, if we look at it, is 53.13 degrees. And it has a positive angle, so the power factor of our total load is now the cosine of 53.13 degrees, and that's going to be 0.6 because it was positive. It's now a lagging power factor, and that now completes or finds all of the parts that we needed for problem number 4.